Hi, we are SpacedOut, where we are immersed in space but grounded in awareness. I'm Preetha, an astrophysics PhD turned data scientist with expertise in data driven problem solving.
I'm Jessica Lipscomb, a double E with a master's in data science, and my thesis dealt with developing transformers to improve the location accuracy from GNSS data. For this year's Space Aware Datathon, the challenge was to enhance space situational awareness using open data. We chose to focus on satellites in low Earth orbit as they are particularly prone to drag risk and orbital decay due to geomagnetic and solar effects. Therefore, we sought to design an early warning system for satellite operators showing how these effects influence their satellites. But there are currently over 10,000 satellites in LEO. So to help scale the problem, we chose to focus on the Earth observational satellites operated by Planet. To determine the decay rate of the Planet satellites, we obtained the TLEs for all of their currently active satellites over the last 6 years using SpaceTrack's API because getting an account was instantaneous. We obtained the geomagnetic and solar data from GFZ-Helmholtz Center for Geosciences because they are the custodians of the geomagnetic data and also provide an account-free API for pulling both their data and solar data already time-aligned. We developed shared notebooks in Google's Colab environment and then used the request library in Python to issue the desired request to each of the API endpoints. We used PyOrbital to parse the TLEs, which we stored in Pandas data frames that we merged with the space weather data based on the timestamps. We explored the data frames, which revealed there were duplications that needed to be dropped. We decided to simply use a daily average of the data, which we used to calculate additional fields such as the decay rate, our target, by differencing the semi-major axis between observations. To help guide the model development, we correlated the orbital and space weather features with this decay rate and categorized specific fields like inclination, altitude, and class of satellite, as these could impact our model.
On finding strong correlations for specific altitude inclination groups, we narrowed down the relevant features and dived deeper into modeling to validate these relationships. We cleaned the data by dropping the missing values and removing the outliers. For mid-altitude satellites, we went a step further and applied k-means clustering to capture the hidden subgroup. Each subgroup is modeled with XGBoost using robust scaling and randomized search CV for hyperparameter tuning. Model performances evaluated here show strong predictive power overall. Subgrouping boosts accuracy for mid-altitude satellites with R-squared reaching 0.92, confirming the value of tailored modeling. We visualize here the feature importance to understand the key drivers of decay risk. Atmospheric drag dominates across all groups, followed by orbital parameters like perigee altitude, semi-major axis, and inclination. Space weather contributes only in low altitude and sun-synchronous orbits. Using regression uncertainty, we then estimate risk levels and integrate them into an early warning system.
Here you can see a demo of the prototype early warning system we developed using Gradio and Python that allows a user to see the altitude and inclination group associated with a specified TLE and obtain the predicted decay rate and associated risk of decay on any given day. The user has the ability to choose from the data in our catalog, which we use to train and test our model, or to upload a single TLE of their choosing. If a user uploads a TLE, we will parse it, compute the extra features we need, and automatically pull the associated solar flux and geomagnetic activity index readings for the associated day before submitting the features to our XGBoost model for prediction. As the TLE providers we encountered require accounts, we chose not to enable automatic downloading of any TLEs. By using our tool, satellite operators can more quickly determine if the risk of decay for their satellites has increased, allowing them to make adjustments earlier. As we had to scale the problem down due to time and resource constraints, the next step would be to see how well the model performs on other operator satellites. We also wish we had the time to look at developing time series models that could help predict the decay rate into the future to provide even more advanced warning. Another area of exploration is the impact an increased decay rate has on the quality and continuity of the critical data and imagery satellites deliver. In terms of recommendations, we'd like to see satellite operators use our early warning system and maneuver their satellites earlier, as soon as they start to be classified as medium or high risk, in order to increase the satellite's lifetime and therefore limit the amount of space debris in orbit. We also hope this work helps raise awareness about the importance of space weather and its impact on satellites that so many of us depend on daily. Through this process, our awareness of the impact of space weather on satellites, especially those with lower altitudes, has increased, and we hope our model can be used to extend the lifetime of LEO satellites and limit the amount of space junk.